did a last lesson of chapter 6. We're going over applications of rational equations today. So sort of real life scenarios where when you model them, you get a rational equation and then we need to solve it. We're going to see three main types of scenarios today. And the first one is a distance, speed, time scenario. If you're not a physics student, you may not be as familiar with distance, speed, and time equations. So I'm going to give you a little triangle to help you remember them. We set it up like this: distance, speed, time. And whatever one you want to solve for, so let's say you want to solve for distance. Then you would cover the d up and it shows you exactly what you need to do. So distance would be speed times time, since they're right next to each other. Let's say now you want to solve for speed. You would cover speed up and it would be distance over time. So speed is distance divided by time. And then covering time up, you'll see it's distance divided by speed. We're going to use this one in the example. The other thing we're going to do is, as we read through the example, we're going to set up a little chart with distance, speed, and time. This just help us organize the information that we're given. Okay, so Mario drove to Grand Prairie and back, a distance of 300 kilometers each way. So that's our distance. Edmonton to Grand Prairie, 360. Oh, sorry, I said 300, 360. And then Grand Prairie back to Edmonton, also 360. Okay, now let's look at the speed. It says Mario's average speed was 30 kilometers per hour greater on his return trip than compared to his trip out. In a question like this, typically you're going to have something that you don't know. So they don't actually tell us what his speed was on the trip out or there. They just tell us that on the way back, it's 30 kilometers per hour faster. So let's make a variable here. So whenever you don't know something, make a variable. Let x be the speed on the way there. So his speed on the way there is going to be x. We're not told what it is. I don't like to use the variable s for speed just because it looks like a 5. So I prefer using x. And then on the way back, we're told that it's going to be 30 kilometers per hour faster. So it'd be x plus 30. Okay, and then the time, let's see what they say. Total driving time was 10 hours. So when you add these two together, it's going to equal 10. But they don't tell you what the individual times are. That's where our distance, speed, and time equations are going to come in handy. We have here that time is distance divided by speed. So for this first leg of the journey, it would be distance, 360, divided by speed would give us the total time. And then here, 360 divided by x plus 30 would give us the total time. And when we add those together, they should equal 10. So that's our equation. I'm going to write it right here. So 360 over x plus 360 over x plus 30 is going to equal 10. So this is the equation we're trying to solve. And so that's kind of the hard part, is setting it up. And then once you get to here, it's really a 6.5 question where you're just solving this rational equation. So we can recall back to 6.5 and see what we need to do when we have fractions in our equation. We want to multiply by whatever the denominator factors are to cancel them out. So we have a factor of x and x plus 30. So that's what I'm going to multiply every single term by. X and x plus 30. I'm going to zoom in here so we can get a better view. Okay. And let's cancel things out. So the x's will cancel there. I'll have 360 times x plus 30. In the second one, the x plus 30 terms will cancel. So I'll have 360x. And in the last one, I'll just have 10x times x plus 30. Okay, let's expand all of these out and put all the terms to the right-hand side. So I'll have 360x plus 30 times 360 is 10,800. And then another 360x. And on this side, I'll have 10x squared and 300x. Okay, so let's move all the terms to the right-hand side. This is a quadratic equation here. The numbers are going to be pretty big. So I'll have 10x squared minus 420x when you move all the x terms over, and then negative 10,800. Luckily, I can factor out a 10. That reduces the numbers I'm working with a little bit. 1,080. Now, to solve by factoring, the numbers are pretty big, and you can guess and check some numbers. The two numbers that multiply to negative 10,080 and 42 are, I believe, 18 and 60. Negative 18 and 60, yeah. But you can solve this using the quadratic formula as well. Just because the numbers are so large, it can be hard to factor. But I will factor it here. But you can use the quadratic formula as well. X minus 18 and x plus 18, x minus 60. Yes, those two numbers add to negative 42, and they also multiply to 1,080. Perfect. So I have two possible solutions. Either the speed was negative 18 or the speed was 60. Now, a negative speed in this context doesn't make any sense. Speed is only a positive number, so I'll just put not relevant. You can't have negative speed. So this is the final answer. The speed on our way there was 60 kilometers per hour. We should always write our final answer as a sentence with proper units so that we understand the context of the problem. Okay, let's try one more like that. Another distance, speed, time scenario, because they can be set up in different ways. So I want to show you one more scenario. A really common one has to do with boats and currents. Also, you'll see like questions with planes going with the wind or against the wind, the same idea. So if you've never really taken a canoe trip down a river, you'll notice that like one way down the river, it'll be super easy. That's because you're going with the flow of the water. And then on the way back, it's going to be more challenging. You're going against the flow of water. So you're going to go faster with the current compared to against the current. Okay, so now that I've sort of explained that, we're going to look at the scenario here. And I'm going to use this big space up above to do this question. And I'll set up that little table as well. So the table you always want to set up looks like this. It's going to have three lines: distance, speed, and time. And let's read to fill it up. So a boat travels an average speed of 15 kilometers in still water. So this time they're telling us the speed. The boat travels 12 kilometers downstream. In the same time, it travels 8 kilometers upstream. So that's our two directions. We're going to go downstream and upstream. Okay, so they just told us the distances there. Let's read those again. So it said the boat travels 12 kilometers down, and the same, it travels 8 kilometers up. So 12 kilometers down, 8 kilometers up. The times are going to be equal to each other. Okay, and the speed is 15, but we don't know the speed of the current. So if there was no current at all, we'd be going 15 kilometers per hour. But when you're going with the current, you're going to have an extra bit of the current speed helping you. And then when you're going in this direction, you're going to be going 15 kilometers per hour minus whatever the speed of the current is. So when you're going downstream, that means like with the current faster, you're going to be going 15 plus x because you'll have the speed of the current to help you. And then when you're going upstream, that means it's harder. You'll have 15 minus x. Okay, and then time is distance divided by speed. So it's going to be 12 over 15 plus x and 8 over 15 minus x. Now, the way this equation was set up, or the scenario was set up, is said that the two times were equal. So that's why I put an equal sign here, and that's our equation that we're solving. 12 over 15 plus x equals x over 8 over 15 minus x. X is the current speed. That's what we're solving for here. Okay, so let's go ahead and use our strategy of multiplying by all the factors in the denominator. 15 minus x and 15 plus x. Okay, so we'll end up with 12, 15 minus x on this side because the 15 plus x is cancelled. And on this side, I'll have 8, 15 plus x because these ones cancel. Okay, and now I can go ahead and solve this. 12 times 15 is 180 minus 12x. And 8 times 15 is 120. That's 8x. This is not a quadratic equation, so we just solve this by moving all the x terms to one side. So I'll move the x terms to this side. So I have 180 equals 120 plus 20x. Subtract by 120 on both sides. So I have 60 equals 20x, dividing by 20. No factoring to do in this question. X equals 3. So the current speed, the average speed of the current is 3 kilometers per hour, and that's what the question had asked for. So the average current speed is 3 kilometers per hour in this scenario. Okay, great. So every time you see a distance, speed, time scenario, you want to set up a little chart that looks just like this with your distance, your speed, and your time. And then you're going to have a direction going either way, and you want to fill out the information given to you in the question with that. Okay, the next set of types of questions I call work problems. They're about doing some sort of work and how fast you can finish it. So let's read this scenario here. It says, if you take the SATs, these are super common on the SATs, by the way, too. Marissa can paint a garage door in 3 hours. When Marissa and Roger work together, they can paint the same door in 1 hour. How long would it take Roger to paint the door on his own? Okay, so this is what I recommend for doing this. There's not much space here, so I'm going to pop up here. And I'm going to make a similar type of organizational chart. I'm going to have Marissa in my chart. I'm going to have Roger, and then I'm going to have together. And I'm going to have, so I'm going to have different lines here. And then I'm going to have the time it takes them to do the work and like to complete a whole job, and the fraction done in 1 hour or 1 unit of time over here. Okay, so let's fill this chart out. So let's go back and read the question and figure out what we know. So Marissa, to complete an entire garage, so time to complete 1 full garage is 3 hours. So let's fill that in here. We're told that here. Roger's time when he's working alone, we don't know. So let's let X be the time it takes Roger to work on his own. Should always define, if you make a variable, what it is. We don't know that. And we are also told in the question that if they're working together, it takes 1 full hour to complete an entire garage. Okay, now, so for work problems, you always want to set it up like this. You put the times it takes to do the full job, and then let's write down what fraction they would complete if they only work for 1 unit of time. So for Marissa, if she works for just 1 hour, because the whole thing would take her 3 hours, so she would do 1/3 of the job in 1 hour. For Roger, I don't know how long it would take him. Maybe it takes him 4 hours, I'm not sure. But then he would be 1/4 of the job, for example, if it was 4 hours. But we don't know. So whatever that X value is, though, he would finish 1x of the entire job in 1 hour. And together, they actually complete the entire job in 1 hour, so it would be 1. Okay, and what we do know is that these two added together equal the together number. So 1/3 plus 1/x should equal 1. Okay, let's solve this equation. So let's multiply by all the factors in the denominator. So multiply by 3x. So we'll get x plus 3 equals 3x. Move the x over to the other side. We get 3 equals 2x, and divide by 3. Divide by 2, not 3. Oh my gosh, what am I doing? Divide by 2. We get x equals 3 over 2, or 1.5. So let's write our final answer as a sentence. Remember, x was the time it took Roger to do the whole job on his own. So it would take Roger 1.5 hours to do this on his own. What I recommend when you're doing these problems, after you do a few of them, I find students find them quite easy, but the first few times you do them, you'll find them really challenging. That's because of the setup. If you don't set them up in this way, they can be hard. So what I do recommend is maybe have this example sitting in front of you and just fill in the different names that you're given in your scenario and the different times, but set it up the exact same way as I have here. Okay. Finally, the last one is kind of a chemistry sort of scenario when you're mixing things together and you want to create a solution with a certain percentage. This is quite common if you're a chemist, but also common if you're baking and things like that. Okay, so how much lemon juice must be added to 2 liters of water to make a lemonade solution that contains 20% lemon juice? Again, we're going to set up a little organizational chart. It'll be pretty simple. I'm just going to have my lemon, my water, and my total. Okay. Okay. And let's put the volume here. Okay, so I am told that we need 2 liters of water. I don't know how much lemon juice. It doesn't say. That's the point of the question. So let's let the amount of lemon juice be volume of lemon juice. So X. And then the total volume is going to be whatever those are added together. So X plus 2. Okay. Now, what I want to make sure of is that we have 20% lemon juice. So 20%, remember, is 20 over 100. So when I divide the lemon divided by the total, I should have 0.2 or 20 over 100. So let's write that down. Lemon was X, total was X plus 2, and this should equal 20 over 100. There we go. There's our equation, and we can solve it. Okay, so we multiply by any common factors in the denominators. So 100 and X plus 2. So this one will cancel, so I'll have 100X. And then these will cancel, so I'll have 20 and then X plus 2. And I'm just going to solve this. So I have 100X equals 20X plus 40. Move the X's to one side. 80X equals 40. Divide by 80. X equals 0.5. Or you should add 0.5 liters of lemon juice. Okay. And that's it. So those are the 3 main scenarios you'll see: distance, speed, time, work questions, and then these chemistry type questions. So that's the end of the lesson. I'll pause it there.